Thanks everybody for coming. My name is Spoons. My parents still call me Dan, but nobody that I hang out with or work with still does really. I'm an engineer. In a past life I was a researcher. I love to geek out about programming languages and garbage collection. But today I'm going to talk about running and monitoring production software systems, which is also something I'm excited about. Where I work now at Lightstep, we've built a tool for doing distributed monitoring, so I spend a lot of time thinking about this. The tool itself is also a distributed system, so I also care about it from that point of view, and I also participate in a thing called open tracing that I'll mention a couple times during the talk. So what I'm going to talk about, I think, is sort of the essence of monitoring, or I guess if I follow Charity's lead from this morning, observability, but I don't know, I'm not sure I can keep the two of them straight. Really, I'm just really trying to go, understand for our software systems what's going wrong, where's the problem, and why is that happening? And I think anyone who is responsible for production systems cares about these questions, and they want to find answers to them quickly and with confidence, and with as little investment as possible. And I think it's a real opportunity for us to do better in terms of the tooling we have, but it requires us to think a little bit more broadly about first kind of the existing tools and the way we've kind of maybe segmented them, and then secondly about the way that we collect and analyze the data that we have. And so what I kind of hope that you all take with you today is just maybe some questions about how we're doing that, and I'm going to show some examples of how I think we could do better in the future. I think we're here because we like building systems and we like helping others to build systems. That's why I'm here. That's hard. Building systems is hard. If it was easy, we probably wouldn't be here. And I think one of the big challenges in running distributed systems is remediating problems when something's gone wrong. Downtime, broken deployments, those can mean a loss of revenue, a loss of users, they can damage your brand. So the faster you can fix a problem, the faster your users can get back to whatever they were doing, and you can get back to sleep. If you went to Lauren Hochstein's talk yesterday, he said a lot about different kinds of things that can go wrong and how you can do science to understand those vulnerabilities and address them before they become outages. But of course, some things will still go wrong in production. So I think the way I think about it, the purpose of monitoring is to tell stories. I don't think anyone's going to argue with that. Probably some argument about the way that monitoring tools do that. Maybe that's why some people came this weekend to argue about that. But I think if a monitoring tool doesn't tell a clear story, it's not really working. And ideally, that story takes you to why the problem is happening, and it takes you to a solution to that problem. But there's a number of factors that have led to our tools becoming less effective recently. Some of these might sound a little bit familiar, but I think for monitoring it means something a little bit different maybe. Microservices are here. I don't think anyone's arguing with that anymore. It's great. I'm excited about them. There's a lot of cool things about microservices. But they broke our tools in that each transaction is still a single story, but now not just one storyteller, but a whole set of them. I think this is kind of a big deal, bigger than the move to VMs or the move to the cloud. I think of it a lot more like the transition between desktop software, where we took something out of shrink wrap and installed a DVD or a CD or floppies or something, and transitioning from that to a client-server architecture. The tools that we had that worked for desktop software just didn't work for client-server. I think the shift to microservices is sort of similar categorical shift, and I think there's a similar kind of categorical breakage in the tools that we're using and the workflows that we have. So back in the day, applications looked like this. They were extremely symmetric. No, they were square. They were one square. And maybe that box is broken into a bunch of different libraries or packages, but it all fit together in a single process. And okay, maybe it wasn't one process, maybe it was like 3, but I guess the idea is like everyone in your org probably knew all 3 boxes. They knew what they did. They knew how they interacted. But the idea with microservices is that's not true anymore, right? Like, I don't even know all of the names of the services anymore. There's just too many of them to keep track of. They're changing all the time. That's great now that those things can be deployed independently and scaled independently. Not so great that they're being monitored independently. So it used to be that tracing, kind of old school, used to mean just like following the path of execution through a single process, and that was pretty easy. You just walked up the stack. That's why we have print stack trace. But when you're doing that in a distributed system, it means that you really need to follow that path across process boundaries. And that's not as easy, but really doing that is kind of table stakes for monitoring in distributed systems. If you're not doing that, it's going to be really hard to understand what's happening. I think if you see folks moving towards microservices, even just starting down that path, like I'm not talking Netflix-style things, just like 10 services maybe, and you don't have some kind of tracing solution, it's going to be pretty painful. And again, not even like complicated things like P99.9 latency or anything like that. Just like something's on fire, what's going on? I think tracing is really important for that kind of thing. There's another problem that's kind of come up, maybe not quite so recently, but there's a lot of things happening, and I would like to imagine in my simple single-core brain that requests are atomic and serialized, but they're not. Of course, there's a lot of, for performance and other good reasons, a lot of things happening at the same time. And that's not quite true either. There's a lot of asynchronous things happening. Requests get interrupted, they perform I/O. Maybe you're using some sort of framework like Node, or you're using Go routines. There's a lot of stuff happening. A request will start, it'll pause for some reason, other things will run for a while, it'll come back, and so on. In a distributed system, you've got all of that, and it's worse. You've got all of that in every process, and now you've got single transactions spanning multiple processes. And even that picture itself is kind of an oversimplification, because everything, if you look kind of closely, is still a linear thing, generally, and the whole part of the reason you're doing this is so that you can fork off parts of a request, do the processing in parallel, and then join the results back together as you go back up the stack. I sort of ran out of room on the slide to do that, though. Anyway, the goal is to connect all that stuff back and then isolate one of those requests so you can actually understand what's happening and try to address the problem. Yeah, and we can do that, but I think I'll have a chance to say a little bit more later about maybe why that isn't quite enough. So anyway, that's sort of where we are. I think those problems are not going away, so now the question is sort of like, how are we going to deal with them? And that's where tools come in, and I think, like I said, tools are going to kind of try to address these three questions, and that's how I'm going to try to structure the rest of the talk. Okay, so what's going on? Answering these questions actually not so bad today. We've got some pretty good tools for doing this. So we can use metrics tools for measuring symptoms, and symptoms are a pretty good way of modeling what's going on. So you can make a metric that associates with different end-user experience. That could be latency, it could be errors, it could be a few other things. And then you can set SLAs or goals around those metrics, and set an alert or notification when you miss your goal. And I should say I wrote end user here. End user might be an actual human being. If you're a platform, your end user might be either an app or another application that's built on top of you. But the point is that you can model pretty easily what your immediate clients are seeing using metrics. So how do we explain anomalies with metrics? So we might have something that looks like this. I just grabbed some random thing from one of our internal dashboards. So I don't know if this was error rate or something like that, but something's up about 12:30. Better figure out what's going on. Nothing was pushed out then, so let's dig a little bit deeper. Luckily, we use tags, as most metric systems support, to tag based upon things like customer, service, what VM it's running on, things like that. And then we can do a group by of the data to actually break that apart and drill down and see what's happening. So that's cool. So now you can see, I think, that most of that bump actually can be attributed to this this one component. We can look at the tag that thing represents and understand what's up with that customer or service or VM or whatever. So that's great. We've gotten somewhere. But this is kind of a big problem. Charity mentioned this morning. We say cardinality sometimes. I feel like this is a pretty big word to talk about a pretty simple thing, but just the idea is some tags have a lot of values, a lot of different values. And when that happens, it becomes really expensive to collect that data, really expensive to manage it. And when I say a lot, I mean more than 100. And it's not uncommon if you have a customer ID to have obviously hundreds of thousands or millions of values for these tags. So yeah, that can be a problem and means that maybe this is not quite so useful. But that's sort of one problem. The second one I want to say is this is not a diagnosis. We have a smoking gun here, but we can sort of narrow a little bit. We don't know, why that customer is misbehaving, what that service is doing, or what's wrong with that VM, right? So at some level, it's neither scalable nor actually delivering what we really want here. Another problem with metrics is you start to get dashboards that look a little bit like this, and that can be a little bit overwhelming. Having lots of metrics can seem great, but I think it's important not to confuse having lots of answers to the what question, not to confuse that with an answer to the question of why something has gone wrong. We used to have giant dashboards like this in the teams I worked on at Google. They were really cool and they looked pretty impressive, but the thing is, unless you were an expert in the system that was being described, like the dashboard was not that helpful, right? So I don't know, I just, so I should admit I still use dashboards. Not everybody's perfect. This is some random metrics that I grabbed from our service, and we had an incident here. It wasn't terrible, but it wasn't great. I don't know, anyone can help me out with the root cause here? Like upper left, lower right, anything like that? Yeah, so you can see correlation pretty easy in something like this, but it's really hard to determine causation. And that's really what you want to do. In distributed systems, you have lots of interconnections between these things. It's quite common for lots of metrics to blow up at the same time. Actually, I don't really remember what this is about either. Like, this dashboard has changed a lot, these services changed a lot, and that's kind of leads to the next problem, which is that the number of metrics, if you talk about your business in terms of what matters to your customers, like, that should stay relatively small. Of course, with feature changes, you might care about a few more, but as you develop more and more microservices within your system, you'll sort of be tempted to create more and more metrics. And that's a problem for a bunch of reasons. One, that's just a lot of maintenance, like that dashboard is outdated, that's no good. It can get costly from a storage point of view, even before we get to talking about tags. There's just, if the data that you have is scaling both with the number of customers and the number of microservices, or the number of transactions, like, that's not great for your business. And I mean, this is only going to be helpful if you actually define metrics for all of the root causes, which you didn't, right? There's some root causes that you haven't seen yet, and so it's hard to anticipate what those are going to be, and you're not going to be able to use metrics to find those. So in the end, metrics are not really the answer to root cause analysis. They're useful, but they're not the end of the story. Okay, so chapter 2. Where is the problem in my system? In this, and actually most of the talk, I'm going to talk a lot about latency, but this could apply to errors or other kinds of things that you might measure as well. So, okay. Figuring out where our problem is, this is sort of classic distributed tracing. How many people here do distributed tracing? Like doing distributed tracing? Have heard of distributed tracing? Okay, cool, awesome. I guess that's why you're here, maybe. So at Google, we had this tool called Dapper, and it was pretty good for this kind of thing. So you'd get paged, you'd have some metric that said end user latency was up. You'd log in, and you get Dapper up. It'd tell you where the latency came from, and you do kind of critical path analysis, and then you kind of go from there. So I want to do a little bit of illustration. So I have a kind of side project with one of my co-founders we call Donut Zone, which is a donuts as a service solution. We're doing some blitz scaling right now, kind of experiencing some hypergrowth, but we're microservice oriented, so we're pretty ready to deal with that growth. But we are having some latency problems, and we use open tracing, so it turns out that we can integrate with a bunch of different tracing vendors pretty easily. So let me just give you a picture of what our architecture looks like. We have 3 different clients. There's a client that you use to order donuts. We have a couple administrative clients that we use for either restocking the ingredients or cleaning out some of the equipment. Those all talk to an API service. API service then fans out to some other backends. So we use BrainPail for payments, and then we have a Topper service and a Fryer service that are also doing a lot of the heavy lifting. Because we're real computer scientists, and we want to do it right. We use mutexes around the resources that are here. So we don't want to be cleaning the fryer where you're frying donuts. You don't want to be restocking the shelves while you're trying to grab the toppings. Like, it's going to make a mess. So we've got a couple mutexes in the system, and wherever you have mutexes, you're going to have queues. And so, I mean, this is all as a toy, but what I want you to think about is, like, there's queues everywhere. Whether that's mutex, a database table, a network link, a processor. These are all sort of resources where you can have some contention. And I mean, this is tiny at some level, but I hope it's kind of real enough that you can squint and suspend your sense of disbelief enough to kind of believe it. So, okay. I'm a little hungry. I'm going to order some donuts here. So this is kind of part one of the demo. You guys are going to have a chance to participate in a bit, but let me kind of mess around with Donut Zone first here. Okay, so Donut Zone, here we go. Let's see what we got going on for donuts. We don't have an internet connection though. This is going to be a little bit of a problem for my demo. Sorry, I should have checked this. Give me 1 second. Okay, so I'm going to order some donuts here. All right, super. Cool. All right, what do I want? Let's have some chocolate donuts here. Grab a couple of chocolate donuts. There's a little thing on here that kind of shows you how it's doing. And then I'm going to flip over here to my tracing system and check out how chocolate donuts are doing here. So let's see. So I got some examples. Yeah, these ones took a couple of seconds. That's pretty long for a donut. Oh yeah, of course. Thank you. How's that better? Okay. So this is a trace describing what's going on here. So you can kind of read this a little bit like a Gantt chart. So time's going from left to right, and then kind of down the stack as we go. So you can see each of these different bars here corresponds to different operations. The top one is the browser's kind of view of the world. Then we hit some backends. In the Dapper terminology, these are called spans, but a span is really just a timed event at some level. Anyway, the idea is that we can kind of look and see, okay, there's some time kind of spent on the client, but then like this pink part here, this is really the problem, at least in this case. You can take a look at some of these other ones and see what's going on. Yeah, the fryer really, we sent a second in the fryer here. So, right away we've gone from, user visible experience is not great to we know what component of the system we need to be looking at, and that's great. So we've made some progress. And this is like a tiny little example. Like in the real world, these things can have hundreds or thousands of spans, and so being able to automate finding of the critical path is really helpful and really like gets you going in terms of finding a solution. Okay. So yeah, so this was great, but sort of a gap here, which is like, and this is where Dapper kind of stopped, and where most other tracing systems stop. It would be great to understand why that thing was slow, and it would be great to do that in a kind of general and automated way. And this is sort of the last part, but I want to do kind of a brief aside on tracing and why it's hard. So really, tracing is just logging at some level. We kind of call it tracing. It's special in some way, but like in monitoring generally, there's sort of two things. There's statistics and there's events. And events maybe includes tracing and logging, but I think when people say tracing, or at least distributed tracing, really they mean there's some kind of maybe sampling strategy that's a little bit smart maybe, and then that they can see some kind of causality or structure on what's happening, not just timestamps. The problem with logs, I had this diagram here for one transaction. Oh, sorry, you guys can't see this. Here we go. Sorry. Yeah. So tracing is, excuse me, one transaction, but a lot of logs for that. So I guess you don't want to put your developers in a position where they don't want to log. Like logging is a valuable thing, but if you're logging a lot, for every microservice on every transaction, that can get pretty expensive, or even just kind of infeasible from a sort of a throughput point of view. So really, this was the idea of the problem that Dapper was solving at Google, is they wanted to do logging for web search requests, but even the public numbers for Google are something like 2 billion requests a second, so there's just no way to log all of that data. So the solution was basically to throw out 99.9% of it. It turns out that like 0.01% of 2 billion is still pretty big. You can still find whatever signals you're looking for in there. But you have to do that in a kind of smart way in that you want to make sure you capture the whole transaction so that it's still useful. But if you take the number of transactions, like I said, and just do it naively, it'd be pretty expensive. Let's talk for a minute about sampling. There's really kind of 3 points that you can do sampling. One is you can do it in the process to limit the impact on CPU. You can also do it in process to save network costs. And then once you've sent it over the network, maybe you buffer it somewhere and do some more sampling to limit the cost to durable storage. In the end, the one that really matters is just the last one. Like, this is really the only reason that we did any sampling at Google. Only for the most high throughput services did we ever see any impact on the CPU. And really, that's really about throughput, not latency. Like, there's a way generally to move all of this kind of instrumentation out of the critical path itself and not have really any impact on latency. And the throughput was really only a small %. And that was fine for everyone except for like the biggest parts of web search. So sampling in the process is really not necessary. I think that's really important to understand, because if you're not sampling in the process, you can make much better decisions about what you choose to keep or not keep. Of course, you don't want to write it all to disk. That's crazy. And there's some tricks to making this work. But there's a big gap between tracing systems that do a lot of this, what I think of as kind of more naive sampling, and where they really should be, I think. So, okay, this gets us back to the last part of the story. Understanding why. So I had this diagram before where I was trying to isolate distributed transactions. It's not really true. Like, they're not really independent. So, you know, yeah, and the rest of the demo, I think the reason I need your help is to show that. So I have this hypothesis that most latency issues are actually due to contention for shared resources. And that means when I'm looking at a trace, I see that there's a slow span. That request is actually not the problem. The problem is some other request that's happening at the same time. And I tried to frame this in a kind of stark way, like maybe not most, but I think it's probably most. And I think the reason I wanted to do that is there's kind of a blind spot in our tools, and I think that also biases the way we kind of think about the problem. Like, tools are pretty bad at understanding what's happening in other transactions at the same time, and I think that we kind of internalize that in a way that makes us think that it's maybe not that important. Yeah, so I had this thing before about independent tracing, but really the red pill reality that we really live within is that these things are all interdependent. Okay, so you know, I have this doughnut as a service thing that I'm running. I need to understand what's going on. So here's what I did. I assigned what I call resource identifiers to all of the important resources. This is really just, I took a small wrapper around the mutex library in Go. It's like 50 lines. And the actual application changes, I'll show you in a second, but it's usually like 1 or 2 lines. We then tag all the spans with that resource ID whenever they try to grab that resource or use it. And then 3 is sort of the magic part where we figure out how there's some interference between these things and capture that. And then, you know, if we've done that, then we can answer the why question pretty directly. So, like I said, the code's, it's really not that interesting. So this is like, you know, drastic oversimplification of how you might write some like thread-safe code and Go. Of course, you want to defer that unlock or something like that. Maybe do something between lock and unlock. But really, the only change I had to make here was, one, to wrap the lock itself. I was explicit about the tracer itself. That actually can be done with a singleton, but I just wanted to be clear. And then, you know, when I lock, I actually have to pass the context in so we can figure out how to associate this with a request. So it's pretty easy. Smart lock itself, like I said, it's like 50 lines. It's not that interesting. It's just about generating a random number, really. And that's it, right? So this is how it's going to kind of go. So I'll give you a little preview of what it's going to look like and what's going to happen behind the scenes. So this is one of these traces, right? And we've got this long child span. That's the problem, right? This long one that's kind of in the middle here. And we have a resource ID that is going to be associated with that, this sort of random number. And then what we're going to do when we notice this happens, we're going to go and find all of the other spans that are contending for that same resource. And then we're going to go up the stack on all of those things and aggregate the data from those. So that'll give us a big picture about everything that's happening at the time, and not just like what's happening at a low level, but from a very high level, like a user point of view about what's going on. And then we'll use it to figure out what's going on. And I think the real beauty of this is the tracing system doesn't really care about the kind of resource or how it works. Like, really, the assumption that the tracing system is making is there. So you can unique ID for this thing, and it can find other spans with that unique ID. And that's really it. So you should be able to apply the same thing to a database, network connections, machine resources, whatever it is. It really doesn't matter. So, OK, let's get back to donuts. This is where I need your help. So this is the weird part where a speaker asks you to get out your phone or laptop. And I want everyone to go to donut.zone. And then I'm going to divide everyone into 2 groups here. So everyone on the right-hand side, we're going to call you Group A. Sorry, middle thing has to be like awkwardly divided. But I'd like you all to kind of order just like miscellaneous donuts. I'll show you what that looks like in a second. I want everyone on this side, that's your left, to order lots of sprinkles donuts. Like, go crazy. Like, you didn't eat lunch today. You really need sprinkles donuts, OK? And so, yeah, let's just see what this all looks like for a second here. How are we doing in terms of? Actually, before, let me just restock a little bit here because we're a little bit low on cinnamon. Cool. OK, so. OK, is everybody ready? Maybe you're already doing it. OK. Well, if you're not doing it, do it right now. Just you guys, miscellaneous donuts, everyone over here, lots of sprinkles, OK? Ready? 3, 2, 1, go. And let's see how we're doing here. All right, that's probably good. Thanks. OK, you can take a break. Not too many donuts. It's not good for you. OK, let's see what's going on here. OK, yeah, so definitely lots of slow things happening. Let's take a look at what's going on here. Let's see. Yeah. OK, cool. 11 seconds. That's not good. Not a good user experience. So let's see here. So this was actually a cinnamon donut in the end, not even a sprinkles one, but it's still really slow. And it turns out, like in the example I did before, that the fryer is really the contention here. What we can do is then I'm going to drill down on that and then take a look at what's going on over here. Try and zoom in. This is a really janky graph layout library that we kind of hacked into this thing. Ooh, sorry. But OK, so here's the thing: is this is basically showing kind of an aggregate call graph going back up. So fry donuts at the bottom here. That's the thing that's grabbing the resource. That always gets called from make donut. Make donut gets called from a bunch of places, based upon whether it's cinnamon or chocolate or whatever. But what we're seeing here is that even though this is a cinnamon donut, that it's contending for a lock that 80%, 79% of the load on that lock actually comes from sprinkles. Right? That was this half of the room. And the thing that's kind of cool about this is I didn't say anything about tags or cardinality or anything like that. We didn't have to make any decisions about any of this kind of stuff ahead of time, right? Like we've identified some important information for these things, but the fact that there could have been 100 different, 200, 1,000 different values for this thing, it wouldn't really matter. We're just doing this stuff sort of in real time and aggregating just sort of based on what was important here. Cool. Ready? OK, so let's go on to number 2. Let me remember to flip this back. OK, so group A, I want you all to keep doing the same thing. Just casually keep ordering. Not right now. You can don't eat too many donuts. It's not good for you. When I say go, just keep doing the thing you were doing. But group B, I want you to go down to the bottom. There's this little restock button here, and I want you to click on restock, and then I want you to restock a bunch of all the things. Right? That makes sense? OK. So everybody ready? I think we can do that now. Ready? So 3, 2, 1, go. Order random donuts. Restock lots of stuff. OK, that's probably good. You can take a break, like I said. You've been working hard, eating donuts. OK, so let's see what's going on here. OK, things still pretty slow. Let's grab a couple of these, see what's going on. So these are, again, we're looking at making donuts here. And let's see. Yeah, well, a little bit of network issues here, something like that. This one's still fryer. Let's take a look at this one. Yeah, fire's still pretty bad on this one, but if I look at the toppings here, let's just imagine for a second that the fryer was actually not the problem in this case, but it was the toppings. In this case, what we actually have is not just one call graph, but two call graphs, right? Because there's not any shared code path between these two things. It's just two resources, right? And this is a thing I've seen come up a bunch of times where you could also be two different teams at a company, right? And not even realize that you're working on the same shared resource. But what this is saying here is like, even though, I'm looking at something that's about making donuts, 65% of the load, sorry, super sensitive. Not doing it for effect. 65% of the load on this thing comes from the restocking team, right? So this is the kind of thing this is meant to show is where you might have a new release of a service that's coming out over here, puts a lot of load on this resource. Now your service is really slow and you don't even understand why. Nothing on your side changed. And the idea of something like this is allow you to go right to that thing and find that answer and be able to go to that other team and say, hey, what's going on? Like, you got to stop doing this, or we got to provision this resource differently. All right, so I got one last demo. I need kind of a volunteer for this one. Does one person want to volunteer? Okay. I would like you to clean the fryer. It's a very generous volunteer. So at the bottom of the thing, there's a button for clean the fryer. I want everyone else to do what you were doing before. So you guys are ordering donuts. You guys are restocking. My one new friend is cleaning the fryer. Everybody do that right now. Just keep cleaning the fryer too. It's been pretty dirty. There's a lot of donuts going on. Success disaster. Okay, that's good. Thanks. All right. So let's see what's going on here. Okay, yeah, not looking good. Pretty slow. Got some 11-second ones here, 10 seconds. 20 seconds. It's not good. We got a lot of queuing going in here. Whew. Got a lot of work to do once I get back home. Okay, so let's look at some of these things and see what's going on here. So, not surprisingly, like 20 seconds waiting on that fryer mutex. And the thing that's kind of crazy here is like this, if I can make it bigger. Yeah, okay. Sorry, it's hard to talk and scroll at the same time. So this is one person responsible for 88% of the load on this resource. And this is actually another thing that can happen as well. Like you can have one bad piece of code, you can have one bad customer, and doing kind of a generic, like look at the whole world and look at just P99 or something like that. Like P99 might show all this problem, but you're never going to like see that one small user, one small service, something like that, that's causing the problem. But if you have all the data, you can do this kind of thing. So again, I think it's really kind of a cool, exciting thing that we should be able to do with the tracing systems that we have. I guess I should say, like, Ben, my co-founder, and I totally hacked this up, so none of this stuff actually works. This is all just like a janky demo that we made, but the theory of it's really, I think, there, that like we have the data to do this. There's no reason we couldn't build systems like this. So I just wanted to kind of scroll to the right screen and wrap up here. So a couple things I think I'd like you to take away. One, think hard. Latency, when you have latency woes, latency problems about resource contention, I think it's more common than we might believe. I think that there's an opportunity to do really sort of game-changing tooling around based on distributed tracing that can enable this kind of real-time contention analysis. And if we can do that, we can really cut down the time to remediate these problems, to root cause these bottlenecks. So we can do that super, super fast by using tools to help us do that, right? I think this is the kind of thing where we should be developing systems that help us be smarter, that help us work better. And I think we really, really can do that. So the very last thing, there's a couple of links on here. If you're excited about tracing, I'd encourage you to visit opentracing.io. OpenTracing is an open standard for getting tracing data out of applications. All the code that I wrote for this donut thing is all just using OpenTracing. And then I like talking about this stuff. If you like talking about this stuff, I'm going to go to the Bridge Tap House after Adam's talk later tonight. If you want to meet up there and grab a drink or something to eat, hit me up on Slack and we can try and coordinate, and it'll be fun. Thanks.